Okay, okay. Mm.
Yeah, did you hear it?
No, I didn't hear it. Is it being recorded now? I didn't hear any message.
Oh, okay. It looks like it's being recorded already,
Okay.
so you can go ahead.
Excellent. Great. Thank you. Thank you so much for the invitation. These are unusual times, but so this is my first Zoom talk. So, and of course, there's some barrier of the medium here. So, if you have any questions, just interrupt me because I do not know if I know how to see the chat window. Yeah, I don't think, I'm pretty sure I don't know how to see the chat window while giving the talk. So, if you have a question, just interrupt me. Okay. Don't wait till the end or anything. I cannot see the chat window. Okay, so this paper is about testing noisy linear functions for sparsity, and is joint work with my my former postdoc Shui Chen, who is now headed to George Mason, starting as a faculty at George Mason in the fall, and Rocco Servadio. So let's start with a very basic question, really. Oops. Okay. This is about the question of solving random linear equations. Okay. So suppose there's an unknown vector W. So imagine there's a vector W, n-dimensional vector, it's unknown. Okay. And the algorithm gets random plus minus one signings of W. So if the vector W is W1 to Wn, the algorithm presses a button and gets like W1 minus W2 minus W3, blah, blah, equals 7. The algorithm presses another button and gets another equation, so on and so forth. And the goal we are interested in, and okay, so in other words, if I want to describe this precisely, the algorithm on every button press gets a random labeled sample of the form X followed by W's inner product with X, where X is a uniformly random vector from the plus minus one hypercube. Okay. And the question I'm interested in first is how many, what I want to, the goal is to recover W. Okay. And an obvious thing is that because we are getting these random linear equations, if you get about n equations, then with high probability, they will all be linearly independent equations. And then you can recover W efficiently. And this is, of course, Gaussian elimination. Okay. So now let's add a twist to this question. Namely, what if you had an additional knowledge about W, namely that the unknown vector W is k-sparse? By k-sparse, I mean a vector which has only k non-zero entries. Okay. Can you, now that you have this knowledge, can you do better? But the model is still the same. Every time the algorithm presses a button, it gets a plus minus one signing of W, random plus minus one signing of W. And it turns out that now you can do much better. In particular, with about order k log n equations, you can recover W efficiently. By efficiently, I mean the algorithm runs in time polynomial in n and k. Okay. So observe that the number of equations you're now using is much smaller than n. If k in particular is a constant, then this is exponentially smaller compared to n. Okay. And this fact that you can always, if W vector W is k-sparse, you can recover W efficiently is the main, it's like the main algorithmic, the starting algorithmic idea in compressive sensing. Okay, so this is, of course, I guess the first works in this area were by Donahoe, and then subsequently, I guess maybe like the way in which I wrote it, this was by Candes, Rhomberg and Tao. Okay.
Anindya, is this algorithm adaptive?
Well, no. So right now the algorithm is not adaptive or anything. The algorithm is getting, the algorithm presses a button and gets a plus minus one signing of W. So, and the claim I'm making is that if you make about order k log n, get about order k log n such random equations, you can recover W with high probability.
Okay, I see. Thank you.
Okay, high probability being over the equations, not like the W. The W is arbitrary. The high probability is over the equations. Good. Any other questions? So actually getting just k log n equations is enough to recover W. If you forego computational complexity considerations, then just getting k log n equations, upper bound of k log n is actually quite easy. So basically the idea is this, that if you just forgo like, the running time consideration, in order to recover W, which is k-sparse, you have to recover two things. First, what are the non-zero coordinates of W? And then on those non-zero coordinates, what is the value? Now, if I were to magically tell you that here are the non-zero coordinates of W, namely W1 is non-zero, W3 is non-zero, W7 is non-zero, and so forth. If I told you the k coordinates where it's non-zero, then it's just like a linear equation in k unknown variables, and you could solve it with k equations actually. So the main issue is like how to find out the sparsity pattern of W. And the point is that observe that because W is k-sparse, there are only n choose k, roughly speaking, sparsity patterns, meaning the positions where W is non-zero. And what you can roughly do is run a tournament, okay? You can just assume that, you just iterate over all the sparsity patterns, and for each choice of the sparsity pattern, you think it is correct, try to solve what the value of W would be if that you guess the correct pattern. And then you can run a tournament and find out the right sparsity pattern. Okay, as in you can just say, if something is not correct, if you guess the wrong sparsity pattern, it's actually easy to show that then the equations won't be consistent. Okay, so getting a k log n equations is not hard actually. To run the tournament over n choose k possibilities, you require log of that number of samples, and log of n choose k is roughly k log n. However, the running time here is n to the k, because you have to iterate over all possible choices of sparsity pattern. And of course, the big work in compressive sensing is how to not run in time n to the k, but polynomial in n and k. So hopefully that made sense. Are there any questions? Okay, so if there are no questions, okay, so this was just introducing the starting point of this work, but this paper is not about actually compressive sensing, but actually a slight variant of this question, namely, okay, oh sorry, I already, sorry, I said in words what is there in the slides. All right, I should mention here that actually while the work of Candes, Rhomberg and Tao, while it works in our setting, namely the equations are plus minus one random signings of W, actually a much weaker property of the equations is required. They don't need to be quote unquote random linear equations. They need to satisfy something called the restricted isometry property, the RIP property. And actually that itself suffices for an efficient algorithm. But we are not interested in the recovery version of the question. What I'm interested in is the decision version of the problem. Namely, so far we were assuming that we were given the promise that W is k-sparse, and we were trying to recover W. But what if I considered the decision version of the problem? Namely, you have an unknown W. For simplicity, you assume that the 2 norm of W is 1. This is just for normalization's sake. This is not strictly required. And then the algorithm again is the model is the same as before, namely the algorithm receives random samples of the form x comma w dot x, where x is a randomly chosen element of the discrete cube. And the algorithm just wants to distinguish between the following case, that the vector w is k-sparse, or the vector w is actually at least epsilon far in L2 distance from every k-sparse vector. So earlier in the recovery question, we were thinking about a promise version. We were told W is k-sparse and we were trying to recover W. Now we are trying to solve a decision version of the problem. Is W k-sparse, or is W epsilon far from every k-sparse vector? Okay. So, and what is our hope here? So let's see the hope. Let's go back actually a slide. Namely, in compressive sensing, we saw that k log n equations suffice to recover W. Now, even if k equals 1, this number is log n. And it's easy to see that log n equations are always required, because at the end of the day, if you want to recover W, okay, if you want to recover W, you have to recover the non-zero coordinate of W. But the non-zero coordinate of W is 1 among n possibilities. So it requires log n bits of information to come your way. Okay. And you can set up this thing in a manner so that every equation just gives you one bit of information, which would mean that then that would mean that log n equations are absolutely necessary to recover W. So this log n dependence is tight. And in fact, turns out that essentially k log n dependence is also tight unless k is super large. Okay, but what I wanted to argue is that you cannot get rid of the log n if you want to recover W. But now in this decision version, observe, I'm just trying to solve a decision problem. I'm just trying to decide whether W is k-sparse or it's not k-sparse. So per se, there is no reason why this log n must be required. Okay. In particular, what I'm trying to say is that we just want to distinguish between W, which is k-sparse, and not k-sparse, and not per se learn W. And the high level question I want to ask is, can we solve the decision problem with fewer samples than the recovery problem? It is not very hard to show that if you can solve the recovery problem assuming W is k-sparse, then with those many samples, you can also solve the problem of distinguishing between W, which is k-sparse, versus far from k-sparse. So so at a high level, I'm saying that the learning complexity always upper bounds the testing complexity. This should be familiar with most of you if you have thought about these kind of questions. But what I'm asking is, can you do testing in this setting with samples fewer than learning? Can you do testing asymptotically faster than learning? That's the question I want to ask. Okay, let me pause here for a second and see if there are any questions.
Yeah, so I have a question. So you're trying to cover the case where this k log n is not necessarily true?
Yes. Yes.
Okay.
Yeah. So yes. Okay. So yeah, the high level questions, I'm just asking, can we do asymptotically faster than k log n? Or can we do faster? Is there some sense in which we can do faster? And our main result is that it's yes, in a certain sense. I'll say what that certain sense is actually right now. Namely, at least the problem I just described over the hypercube, we will solve it with k over epsilon to the order k samples. Now it actually looks quite worse in k, right? I mean, it's like, it's exponential in k. We do not know if that is necessary or not. But the important thing is that it's completely dimension free. It's completely independent of dimension n. The number of samples you require does not depend on n at all. And while I kind of argued earlier that if you wanted to recover, you had to pay a log n dependence for constant k also, for even k equals 1. Here we are not. So our main result is, this is not our main result. This is a corollary of our main result. The main result is much more general, but this is a high level message. Okay, that sometimes in this setting, testing can be done faster than learning in a certain sense. Okay. And so the dependence on the sparsity parameter k deteriorates. I'm not sure whether this is tight or not. That's what our analysis gives. But most importantly, the dependence on n vanishes. And again, in a very strong sense, we are not learning the vector W, because even knowing one coordinate of W would have required me log n bits to specify. So really, we are not learning W. We are doing something else. We are testing in a very different way. Okay. And I will say a few more things. So our result would in fact also handle noisy samples. What do I mean by noisy samples? So instead of the algorithm receiving elements of the form x comma w dot x, it will receive samples of the form x comma w dot x plus eta, where eta is an independent noise known to the algorithm. Okay, so let me say what I mean by this. So the samples that the algorithm receives would be of the form x comma w dot x plus eta, where eta is an independent distribution and it will be drawn from eta. The distribution of eta, the distribution of the noise might be something like n01, the standard Gaussian or something. So the distribution of the noise would be known. It's not that the noise added would be known, otherwise I could have just subtracted it, but rather the distribution of the noise would be, if the algorithm would be told what is the distribution from which the noise element is sampled, then it's an independent distribution. Okay. And I should mention for the sake of completeness that even the result of Candes, Rhomberg and Tao also holds with noisy samples. Okay, so in this sense, both the result type of recovery and testing results can handle noisy samples. Did the noisy samples, what I mean by the noise being known, make sense? I'm just saying that the algorithm would be told that the label is of the form w.x plus eta, where eta is drawn from the standard Gaussian. That's all it will be told. It will not be told on this sample eta evaluated to 0.5, on this sample eta evaluated to 0.7. Not that, just that eta is being drawn from a standard Gaussian, or eta is being drawn from a Poisson or something like that.
Hey, Anindya, sorry I was a bit late, but does it have to be Gaussian, or can you handle like other noise?
We will handle all sorts of noise. All that will require is that all the moments should be well defined. All its moments should be well defined. It should be finite.
Got it. Thanks.
In fact, it will be like you don't require all, but up to a sufficiently large level. So yeah, something like what Cauchy distribution might be a trick, or something like that might be a little tricky, but everything else will be fine.
Anindya, is there any lower bound for like, I don't know, like adversarial noise or?
Yeah. So I'll get to the like, you know, what if I'll get to the like, you know, maybe I'll answer your question in like a couple of slides, like, you know.
All right, thank you.
Yeah. Any other questions? Okay. So I should say, like, you know, there are two ways one can, like, you know, the two starting points of this work. So one is like this long line of work in the area of property testing, where the main thing is property testing of Boolean functions in particular, where the main distinguishing feature is that the algorithm is given query access, so much stronger form of access to an unknown Boolean function. And the kind of questions you want to ask is, does f have property p, or is f epsilon far from having property p? Okay, where property p is some property of Boolean functions, and epsilon farness is measured in Hamming distance. And in this area, a lot of non-trivial results are known. I would like to highlight one. For example, if you want to know that whether your given f is just a function of k variables, what would be referred to as a property of k being a k junta, so Eric and Amit know all about it. Then this can be decided, this property can be decided with just order k queries. So completely independent of dimension n. So this is like a kind of like, you know, target we are also shooting for, which is very much inspired by property testing. Like, can we do it completely independent of the ambient dimension? Okay. But of course, the big thing is that this area of property testing assumes query access. On the other hand, they of course get much stronger guarantees in a sense, which might be a little technical to get into right now. But like basically, yeah, like here we are assuming it's the function you are getting is a linear function, and you're trying to decide whether it's sparse or not. But in property testing, you just say you're getting some function. You do not say it's a linear function, now decide if it's sparse or not, or if it's, in property testing, you have a much stronger form of access, but a much stronger form of separation guaranteed. Here, you are assuming sample access, but able to guarantee something much less. The second strand of work from which this work derives its inspiration is this notion of, is this like, you know, this line of work, mainly from statistics, which I'll refer to roughly as sublinear algorithms in learning. I've just cited two works, but there are like hundreds and hundreds of papers here. I've just cited two works. So for example, there's a recent result of Kong and Valiant from like a couple of years ago now, where the algorithm, well, this is the setting, that the algorithm receives labeled samples of the form x comma w dot x plus eta. Okay, so similar to us. But the distribution of the noise eta is not known. So you do not tell the noise distribution, you do not tell the algorithm, hey, this is a Gaussian, or this is a Poisson, or this is a uniform random variable. You do not say anything, just that the noise is independent of the data. And what the paper wants to do is that it wants to learn the variance of eta. So in some sense, you should think of this as asking how much of you're seeing some response variable w dot x plus eta, and the question you want to ask is how much of the output, how much of the response can you explain by a linear function, which is w dot x, and how much of it is just noise. And what they show is that when the distribution of x is isotropic, when the distribution of the data point is isotropic, then you can estimate the variance of w, or you can estimate the variance of eta, whatever you want to call it, however you want to think of it, using just root n samples. The cool thing is that you can do it with root n samples, but instead, if I actually wanted you to learn W, you would have spent n samples. So again, in this sense, they're able to do learning much faster. They're able to do testing much faster than learning. They're able to tell you how much of does the response variable look really linear, or is a lot of it is noise, where the number of samples to decide it is much faster than what you would have spent trying to learn W. Okay, so this is also another inspiration for trying to do this sample-based testing. Any questions? Okay, there are other papers here, so let me not get into that. Okay, so now let me first state our main result, the simple version of the main result. Okay, so the most simple version of the main result is the following. Suppose I tell the algorithm that the noise distribution eta is a normal distribution with mean 0 and variance at most 10. Okay, so I tell you it's a normal, and I tell you its mean is 0 and variance is at most 10. And I tell you that W is an unknown n-dimensional vector whose 2-norm lies between 1 over C and C for some constant C. Okay, and let D be the uniform distribution on the hypercube. Then if the algorithm receives samples of the form x comma w dot x plus z, where z is being drawn from the noise distribution and w is this unknown vector, then the algorithm will take number of samples, which is like polynomial in k to the k, so exponential is singly exponential in k, and can distinguish between w, which is k-sparse, and epsilon phi from k-sparse, every k-sparse vector in 2-norm. Okay, so this was the first result I actually stated earlier, so I'm just formally stating that result. Okay, does this make sense? That if you receive if you receive labeled samples of the form x comma w dot x plus z, and you know the noise distribution z is a normal, and you know some bounds on the 2-norm of w, then in roughly exponential in k samples, you can figure out if w is k-sparse or epsilon phi from every k-sparse vector. Are there any questions? This was the result I stated earlier.
How dependent will this be on the distribution? Like, if this has the uniform distribution assumption?
Next slide.
Sure. Okay.
Next slide. Okay. So as Gautam asked, there are 3 things we should look at. There are 3 important features here, or 3 important hypotheses that I'm making in this here. First is that the noise distribution is a normal. The second assumption is that the distribution D is uniform on the hypercube. Okay, and I forget what was the third assumption I'm making, so let me just go with 2 assumptions right now. And the question is, how much can we relax these assumptions? It turns out that you can actually relax this assumption a little bit. Namely, it's okay if the noise distribution is not a Gaussian, but that the noise distribution eta is something which has moments of all the order, and it's specified to the algorithm. So the algorithm is ahead of time given all the moments of the noise distribution. As such, all the moments are not required, only up to a sufficiently large value is required. But let's just say that the algorithm somehow knows the moments, all the moments of eta. Okay. And the distribution D doesn't need to be uniform on the hypercube, but rather it can be any IID product distribution on R to the n. The only condition is that it's an IID product distribution, except it's marginal. So any of its marginals, and all the marginals are same because it's IID. None of them, its marginal should not be a Gaussian. It should be it should be different from a Gaussian on a non-measure 0 set. Okay. If that is true, then essentially the same guarantee holds good. In particular, the algorithm can distinguish between W, which is k-sparse, versus W, which is epsilon phi from k-sparse, with number of samples, which you unfortunately, this has gotten cut off. I don't know how to show this properly, but what this says is that it's order 1, where the order depends on everything but n. It doesn't depend on n. It's dependent on the normalization constant C. It's dependent on the moments of the distribution eta. It depends on the error parameter epsilon. It depends on the constant normalization. It depends on d naught, which is like the marginal on any single coordinate of d. However, it does not depend on n. The number of samples is independent of n. I haven't written how it exactly, and it depends on the sparsity parameter k, but it does not depend on n. I haven't explained, I haven't said what this dependence is. I'm not really going to say it anytime explicitly. You will see why. But the main feature is it can be done with sample complexity independent of n. Any questions, since this is a long statement to parse?
I'm guessing the sample complexity is truly horrendous, right?
It's a tower of exponentials.
Okay.
Actually, mostly it would be like, even, I don't know, like, something, there are places where it will be literally a non-constructive bound. We don't know what the bound is. It's just something independent of n.
Sure, but the main takeaway you want here is that it doesn't depend on the dimensionality.
It doesn't depend on the dimensionality. That's the main takeaway. That it depends on everything potentially, the background distributions, individual marginal, the error parameter, the normalization constants, the sparsity parameter, but not the dimension n.
Another question. So, but this is only for this general case, right? Like because in your first slide, you were saying that for linear forms, and then if you have like IID sample from +1 - 1, you get the nice dependence, like k to the k to the k, right?
Yeah.
Okay.
So this is, you will see why, like, why we will have this horrendous bound. It will, or why I'm like actually saying that at times the bounds will be non-constructive. But this is just like in the general sense, this is what would be required. But for explicit distributions, you will be able to get explicit results, really. Mostly you will be able to get explicit results. Okay. Any other questions? So there's like, I've highlighted the two big assumptions, actually the three big assumptions I'm making. I'm saying that the noise distribution eta is completely known to the algorithm. The algorithm is told, here's the noise distribution, rather here is moments. Second, that I'm assuming that it's an IID product. The background distribution of the data, X, is an IID product distribution. So that's a strong assumption. It's product plus its IID. And the third is that actually the marginal, any individual marginal, is not a Gaussian. It should not be a Gaussian. These are the three assumptions. Okay. Oh, actually, sorry, I should say, like, actually we can do much more. We can not just figure out like whether W is k-sparse versus far from k-sparse, but rather we can quote unquote get a fully noise tolerant version of the algorithm. Namely, the algorithm will tell you what is the minimum distance of W from any k-sparse vector up to plus minus epsilon. So in particular, it can compute the distance of W to the closest k-sparse vector up to an additive error of epsilon. Okay. So in particular, it can tell you whether the distance is 0 or much larger than epsilon. It can tell you. Okay. So it's a fully noise tolerant version of the algorithm. And our main lower bound is actually, I made these three conditions. I stipulated these three conditions. And actually, if you weaken any of those conditions, then you will end up paying a log n dependence. So in particular, we proved three lower bounds. First, we showed that if you keep everything the same, just make D, which is a standard IID n-dimensional Gaussian. Okay, so it's a standard n-dimensional normal. Okay, then the sample complexity must grow like omega log n. So this Gaussian is really not an artifact of the proof. It's really required to get a sample complexity independent of n. The second condition is that we require an IID product distribution in the sense that you can, even with a product distribution where the marginals are different across different coordinates. In particular, we show that if the half of the coordinates are distributed like Poisson 1 and the other half is distributed like Poisson 2, then sample complexity will still grow like omega log n, even when k equals 1. So even D being a product distribution, even a product distribution is not enough, and the background distribution has to be IID in some sense. And third is that we assume that the noise distribution is known, and it turns out that actually, even if you even if you did not tell me the noise distribution, you just said it's one of Poisson 1 or Poisson 2. So you kind of told me except one of two options. Then it is possible to construct an example where the background distribution is something nice like Poisson 1 to the n, and still log n samples will be necessary. So really, we really require all this IID, the marginal Rhomberg Gaussian, and the noise distribution to be known to achieve any little or log n sample complexity. So let me pause here again to see if there are any questions. How much time do I have?
I think you have half an hour more, so because it started at 20, so yeah.
Okay, sounds good. Okay. So any questions about this? The lower bounds, upper bounds, anything? Okay. So actually, let me. So I'm not, the lower bounds are, they're like, I mean, they're like, range in difficulty, but none of them are like super hard to prove. They're like, you have to construct things carefully and then show some lower bound, but they're not very hard to construct.
Sorry, one question about the lower bounds. The number 2 there, do you have to, like, do you assume that even if you know which coordinates are 1 and which ones are 2?
Yes.
Huh.
So coordinates are known.
This is really crazy.
Yeah, somehow like, I will tell you the first and over 2 coordinates are this and the second ones are those, and still we do not know to.
I don't know, these are some really surprising results.
So, okay, so that's the talk I'll focus on. Yeah, go on.
Before we jump to the upper bounds, let me second that comment. Those are really surprising lower bounds. The one that I find surprising is the one, why is Gaussian bad? Is there any intuition for why we get this lower bound for Gaussian?
Yeah, it will become clear once I start describing the algorithm. I don't really have an intuition except like something falls through. Okay, so how you prove the lower bound is actually that, you just try to construct you just try to keep a background distribution of Gaussian and then try to say whether it's 1 sparse versus n sparse, and you can write down the base optimal estimator and it will come out that you will get the log n lower bound. So that's not like, I mean, you can come up with the lower bound, but actually something falls through in the algorithm. So of course, like that something falling through in the algorithm does not mean there is a lower bound, but there will be maybe like, why the algorithm fails is more interesting, and that we'll see like when I start describing the algorithm. Did I answer your question, Eric?
Yes, that's great. Thanks.
Okay. Yeah, the lower bound is not hard to prove, but the algorithm failure is more interesting. Okay. I had a question. Where does the requirement D not equal to Gaussian come from? And I never said what is the precise dependence of the sample complexity on this individual marginal D naught, eta, epsilon, error parameter epsilon, k, which is a sparsity parameter, normalization constant. What is this dependence? I just said it's something dependent on that. What is this number? And I did not answer both these questions, so which I'm going to do now. And to answer both these questions, and actually, first of all, I'll show you the simple algorithm for the hypercube where the data x was coming from the standard uniform distribution of the cube. So I'll show that algorithm, and then I'll show the more complicated algorithm. So to do both of that, I'll require the notion of cumulants. Okay. So I did not really know about what cumulants are until this thing. So I'll recall that. Okay. So what's a cumulant? Okay. So consider distribution X. Okay. So this is a real valued random variable. This is like a one-dimensional random variable. Okay. And we all know what moments are. And so consider a distribution which has moments of all order. Okay. We know what it means. So when you have a distribution, so think of such a distribution. Now you can define the moment generating function. Okay. And moments in some sense can also be defined as the coefficients of the moment generating function. So what's the moment generating function? It's like, look at expectation of e to the xi x, okay? Where xi, it's a variable, it's a power series in the variable xi. And then the kth moment is actually the coefficient of xi to the k times k factorial. So if you look at expectation of e to the xi x, you can write it like this power series. And this, I'm assuming that all the moments of x are well defined. Okay, so that's what moments are. Okay, we know what moments are. Now start with the moment generating function and then take a log. When you take a log, it's called the cumulant generating function. Now, of course, when you take a log, it might or might not be well defined, but think about it. At xi equals 0, the moment generating function is just evaluates to 1. Okay. So the log, so in a very small neighborhood of 0, the log of mx is defined because at 0 it's 1. So if you move in a tiny neighborhood, the log will continue to be defined. Even like a complex neighborhood, okay? Even if you want a complex neighborhood, okay, it will be well defined. And what the jth cumulant is, the jth cumulant is the analog of the jth moment for the cumulant generating function. Namely, do the Taylor's expansion of the cumulant generating function around xi equals 0. Now look at the jth coefficient and multiply by j factorial. That's the jth cumulant of the random variable x. Okay, that's what how it's defined. But that's like, quite like, cumbersome to work with. So let me just tell you the operational thing. Roughly speaking, the cumulants and the moments are in one-to-one correspondence. So the first cumulant is just the expectation, it's the first moment. The second cumulant of a random variable is just as variance. The third cumulant of a random variable is this expression expectation of x cube minus blah, blah. In general, if you know the first k cumulants, you can get the first k moments and vice versa. First k moments have polynomials in the first k cumulants, and first k cumulants are polynomials in the first k moments. If you know the first k cumulants, you can get the first k moments and vice versa. Information wise, they're the same things. But turns out that depending on the context, one of them can be more useful than the other, even though information wise, they're the same thing. Any questions about the definition of cumulants or something?
I guess you're going to tell us why this representation is better in some cases?
Yes, yes. So why is it better? So everybody is anticipating the slides now. So here are the two facts we are going to really use. The third is just something I wanted to point out, but here's the first fact. If x and y are independent random variables, then the jth cumulant of x plus y is the jth cumulant of x plus the jth cumulant of y. Note the jth moment of x plus y is not the jth moment of x plus the jth moment of y. It's not additive. Moments are not additive. Cumulants are. Kind of like the log is there, so that makes it add up. And secondly, if you scale a random variable by c, its jth cumulant scales by c to the j. Okay, this is true if this is true for certain random variables x, even for the case of moments, but it's not always true. So cumulants have this two nice properties, even though the definition looks a little horrendous, is that they're homogeneous and they're linear. They satisfy linearity and homogeneity. But cumulants can be kind of hard to understand. I want to give you an example. For example, if you consider the plus minus one unbiased random variable, so plus one with probability half, minus one with probability half. Its moments are very clear. Every odd moment is 0, every even moment is 1. But if you try to compute the cumulants, then every odd cumulant will still be 0. Kind of every symmetric random variable, the odd cumulants are all 0. But the moment, the jth moment when j is even, grows like j to the theta j. So it's like grows like j factorial kind of. Okay. So cumulants can be kind of like, even though they're very related to moments, the coefficients to go from cumulants to moments can be big, and it's kind of not obvious to understand how cumulants are behaving. Okay. But they satisfy these two nice properties, which is what we are going to use. So let me now describe the high-level idea of the simple upper bound. Namely, by the simple upper bound, I mean the algorithm when the background distribution x is uniform on the hypercube, not an arbitrary product distribution, and the noise distribution is a normal. And I want to then what do we do? How do we distinguish between W, which is k-sparse, versus W, which is far from k-sparse? So the thing we do is actually we do something super simple. So remember, what's the setting here? The algorithm gets labeled samples of the form x, comma w dot x plus z. Z is being drawn from a standard normal, or from a normal with variance at most 10 or something, and x is drawn from the hypercube. So first thing we do is we completely ignore x. We just look at the random variable which is the label. Let me call it y, which is y equals w dot x plus z. Now, because cumulants are homogeneous and linear, I can say that the jth cumulant of y is the jth cumulant of z plus the jth cumulant of w dot x. But w dot x is nothing but summation wi xi, where each xi is a Bernoulli half random variable, right? Half probability 1, half probability -1. So again, applying linearity and homogeneity, you get that the rest of the term is summation I equals 1 to n, wi to the j, so wi raised to the jth power, times the jth cumulant of the Bernoulli half random variable. Bernoulli half, I just mean the unbiased +- 1 random variable. Okay. And now, doing a very sophisticated mathematical move, I will subtract the left hand side from the right hand side, or rather the right hand side from the left hand side. So I'll get that summation wi to the j is the jth cumulant of y minus the jth cumulant of z divided by the jth cumulant of Bernoulli half. Okay. Observe summation wi to the j is, we all usually typically refer to as the power sum symmetric polynomial in w1 to wn. It's a jth power sum symmetric polynomial. Power sum symmetric polynomial. So far, so good.
What j does this hold for? Can this hold for any integer j, or?
Yeah, this is for any integer j.
So
jth cumulant. So any non-negative integer.
So 0,
J.
for example, counts.
Let's see if 0 counts. I don't know what the zeroth cumulant would be. J greater than equal to 1.
Okay, fair.
J greater than equal to 1. So the only thing is I divided stuff. So when I'm dividing stuff, I better be sure that the jth cumulant of Bernoulli half should not be non-zero, should not be 0. So in particular, when I'm dividing by half, when I'm dividing by the jth cumulant of the Bernoulli half random variable, I have to ensure that j is even. If j is odd, then this denominator is 0. Because, right, I said this, if j is odd, then the jth cumulant of the +- 1 unbiased random variable is 0. So this equation only holds when j is even. And it will actually, even is not clear, but it will only hold if the jth cumulant of Bernoulli half is non-zero. So certainly j cannot be odd. But you can calculate and show that if all the even cumulants of Bernoulli ± half random variable is non-zero. So this holds for all even j greater than equal to 2. Okay. So I've highlighted the equation again. And now observe something. See, z, which is the noise distribution, okay? Okay, so what do I know? I know that kappa j Bernoulli half, I know that value, right? There's nothing to calculate. There's nothing like I have to estimate, right? It's a fixed Bernoulli half random variable. I can go and calculate what the jth cumulant of Bernoulli half is. That has nothing to do with the problem in hand. I can just compute that. Y is the random variable which corresponds to the labels. So I can use samples to estimate the jth cumulant of y. I know how to estimate the jth moment of y, so 1 to j moments. If I had them exactly, I could apply the algebraic transformation to go from cumulants to moments. And as such, like, now that I do not have the moments exactly, I can always estimate the moments of y using random samples. And it turns out if you plug everything together, you can show that the jth cumulant of y can be computed to accuracy 1 plus delta using number of samples, which is j to the order j times 1 over delta. So what I'm trying to say is that you can get a pretty good estimate of the jth cumulant of y. You already know what is the jth cumulant of Bernoulli half. And the third thing is that z is being derived from a Gaussian. And now I'll appeal to this fact that actually when you take a Gaussian, its first moment is its first moment, its second moment is its second cumulant is its variance, but third cumulant and onwards, the jth cumulant of a Gaussian is 0. Okay, Gaussian is a distribution for which all its cumulants above the second cumulant is unnecessarily 0. This is what we actually is going to come up again and again, and why we cannot have a Gaussian. It may not be clear right now, but that's what is going to the key fact we are going to use. What I'm saying is that from j to the order j samples, or something like j to the order j samples, you can get a pretty good estimate of the right-hand side because you just need to basically estimate the jth cumulant of y. Everything else, the other term in the numerator is 0 and the denominator is something that you can calculate. You don't need to spend like, you don't need to, this is not something about the data. This you can just compute. So in other words, we can get a pretty good estimate of the jth power some symmetric polynomial in wi's. Okay, make sense? Okay. So for the moment, just pretend that we do not just get a good estimate of summation wi to the j for every j, but rather I get it exactly. Okay, finally there will be a little bit of error analysis involved, but just pretend that I get summation wi to the j exactly. Here's the thing. By going from j equals 2, going over j equals 2, 4, 6, 8, so on, I can get summation wi square, summation wi to the 4, summation wi to the 6, all the way to summation wi to the 2k plus 2. Okay, so j is now 2k plus 2. And I can get all these very high fidelity estimates of these numbers with number of samples which grows like k to the order k. I'm like, basically I only have to pay for j equals k plus 1. Okay, so I'm just going to pretend that I have these numbers exactly. So the second power sum symmetric polynomial, the fourth power sum symmetric polynomial, all the way to 2k plus 2 symmetric power sum symmetric polynomial in w's, in wi's. Now, what good does it do if I have this power sum symmetric polynomials in W? Remember, my task is to originally figure out if W is k-sparse or it's not k-sparse. So what I'm going to do is that I'm going to appeal to another fact, namely, I can go from power sum symmetric polynomials to so-called elementary symmetric polynomials. So what is the elementary symmetric polynomial? So the jth elementary symmetric polynomial in W1 square to W1 square. The reason I'm doing square is because observe, I'm getting the second, fourth, sixth, so on power sum symmetric polynomial in wi's, or I can also alternately say I'm getting the first, second, third, so on, and so on, symmetric power sum symmetric polynomial in wi squares. Okay, so I can just think of now wi squares as the variable. Okay, and when I'm trying to decide sparsity, whether I'm looking at wi square or whether I'm looking at wi, it's the same thing. I'm trying to decide are at most k of the wi squares non-zero, they are far from non-zero. The squares are the same as the actual numbers. So what is the power sum symmetric polynomial in W1 square to the elementary symmetric polynomial in W1 square to W1 square? The jth one is go over all subsets of size j of 1 to n, and for all of them, multiply wi square for I belonging to S and go over all the sets, sum it up. That's the elementary symmetric polynomial. That's the jth elementary symmetric polynomial in W1 square to W1 square. Okay, so for example, the second elementary symmetric polynomial in W1 square to W1 square is W1 square W2 square plus W1 square W3 square and so on. Okay, and the Newton-Girard identities tell us that actually, again, the information content in elementary symmetric polynomials and power sum symmetric polynomials is the same. If you know the first j elementary symmetric polynomials, you can get the first j power sum symmetric polynomials and vice versa. Now, given we proved that with polynomial in k to the order k samples, you can compute the power sum symmetric polynomials in W1 square to W1 square. That means you can also compute, and again, I'm neglecting the error analysis here, the k plus 1th elementary symmetric polynomial in W1 square to W1 square. Let me pause here. Does it make sense? Let me pause here.
This is very nice. It's very cool.
Thank you. But now let's think about k plus 1th symmetric polynomial. Okay. See, what is the k plus 1th symmetric polynomial? The k plus 1th symmetric polynomial in W1 square to W1 square is that you try out all possible subsets of k plus 1 of all possible subsets of size k plus 1 from n, multiply the wi squares which fall in that set and sum up over all of them. Now, if w is k-sparse, then any k plus 1, when you take any k plus 1 terms, you multiply them, you will get 0 because w has only k non-zero coordinates. So if w is k-sparse, the k plus 1th symmetric polynomial is 0. Okay. And conversely, it's not hard to prove that if the k plus 1th symmetric polynomial in w1 square to w1 square is 0, then w is k-sparse. Roughly, again, I'm using the fact that w is real valued. So there is like, there is no cancellation between wi, like, all the square terms, when you multiply, you only get non-negative entries. So basically, you just want to figure out so these are both true. And in fact, you can prove something much stronger. You can show that if w is epsilon far from every k-sparse vector v, then the k plus 1th symmetric polynomial is at least something. So it's not just that when w is k-sparse, then the k plus 1th symmetric polynomial is 0 and vice versa, but rather when w is epsilon far from every k-sparse vector, then the k plus 1th symmetric polynomial must be at least something, which is independent of n, which is just dependent on the 2 norm of w and the error parameter and so on. But point is, just putting everything together, the point is that the algorithm, that we can compute this number, right? I already said, like, with poly k to the order k samples, I can compute what the k plus 1th symmetric polynomial is. And in fact, I can compute it to very good accuracy. But then I can just check whether it's like, whether it's very close to 0, or it's at least somewhat large. And accordingly, I can tell you whether w is k-sparse or it's not k-sparse. So putting everything together, what we did was we just algorithm get samples of the form wx, w dot x plus z. Z is drawn from a normal distribution. I compute the cumulants. From that, I compute the power sum symmetric polynomials. From that, I compute the elementary symmetric polynomials in w1 square to w1 square. I look at the value of elementary k plus 1 as elementary symmetric polynomial. If it's large, I say, great, w is not k-sparse. If it's very close to 0, I say, w is k-sparse. And the gap that I have in this value of k plus 1 at elementary symmetric polynomial is useful, because at the end of the day, I will never be able to compute anything exactly. I'll have some errors, so it will help.
So Anindya, a quick question. So in this third bullet of yours, so you get this epsilon to the 2k. It's
Right.
just because you're working explicitly with the elementary symmetric polynomial, right?
Right.
Otherwise, you would expect something just epsilon.
Yeah, I think, like, it's I don't know how to get epsilon. But yeah, this is what we get, like, because the elementary symmetric polynomials, we're explicitly using it, so this epsilon to the k comes up.
Okay.
I do not know how, like, again, like, it's entirely possible that for the cube, at least we know that for the recovery problem, the sample complexity is like k log n, or maybe like if you put the dependence on epsilon, it's like k over epsilon log n. So there's no reason to believe why this has to be like an exponential in k, but we don't know how to do otherwise.
Okay.
Okay.
So it feels to me like this is like a method of moments type approach, except on the cumulants instead.
Right. It's a very much like a method of moments type approach. We're just evaluating the moments and trying to derive some information out of the moments, except the moments are not the right thing to do. The cumulants are the right thing to do.
Yeah. Have you seen this done anywhere else before? Or is this like the first time you've seen it? It's kind of cute.
I
Very
don't
interesting.
think I have seen. I mean, cumulants are like, kind of like, the moment feasibility problem, that whether which sequence of moments correspond to which sequence of numbers correspond to moments of a real probability distribution. That's a super well studied problem. But if I ask the same question about cumulants, technically you can first convert the cumulants into moments and then do the problem. But it's not entirely, as far as I understand, it's not like, there's no explicit characterization. I don't think I've seen too much like work with cumulants. I don't think so.
That's kind of cool. Yeah. That's interesting. I'd be curious to see if this type of observation had been used somewhere else. Like the properties that you mentioned, very simple properties like additive and like being able to scale things appropriately. Like, I guess, yeah.
ICA type work. I think ICA, like, I think ICA analysis, where you're trying to, like, characterize which ones are the Gaussian directions and which ones are the non-Gaussian directions.
Right.
There people, because, like, Gauss, again, we are going to see something else about a Gaussian. I guess I'm almost out of time now, but Gaussians are like, something, like, there like cumulant analysis comes up. How much time do I have? Do I have a minute, 2 minutes? Am I -5? What are we doing?
You have 4 minutes, yeah.
4 minutes, okay. So, okay, let me just very quickly like say what's going to happen in the Gaussian, how to generalize. Okay. So the crucial step, like remember, the crucial step in all this was that we were able to compute the elementary symmetric polynomials. Sorry, the power sum symmetric polynomials in Wi square. And for that, what we did really was we did this kappa jy minus kappa jz. So kappa jy we can calculate, kappa jz is something, when z was Gaussian, this is 0. But even if z is not a Gaussian, you know the cumulant, you know the noise distribution, you can know what its cumulants are. You don't need to do any. I mean, if you know the moments of the noise distribution, you know the cumulants. But then we divided by kappa j Bernoulli half, which was very much using the fact that kappa j Bernoulli half is non-zero for every even j. Okay. And let me say, like, what happens if we tried to do the same thing where the background distribution wasn't +/- 1 on the hypercube, but it was actually some arbitrary IID product distribution, say d0 to the n. Well, you will end up with the same kind of equation. Kappa jy, the jth power sum symmetric polynomial is kappa jy minus kappa jz divided by kappa j d0. But what happens if kappa j d0 is 0 for some even j? Then you do not have this equation for that j. In fact, what happens if kappa j 0 is 0, d0 is 0 for every even j? That can happen, in fact, when d0 is a Gaussian. That can happen, that every single cumulant after j greater than 2 is 0. So you never get this equation. And that's why Gaussian is an exception. And then you can ask, can this happen in other settings? And now I'm going to like use a very heavy hammer. So, okay, I have 2 minutes or something, so I'm not going to explain the proof really. But here's the big theorem that we are going to use. Called, I don't know how to pronounce it. I'm just saying Marcinkiewicz theorem. But this M theorem says that you can think about like, the cumulants of a distribution. And there are two possibilities. Either the distribution has infinitely many non-zero cumulants, or the distribution has at most 2 non-zero cumulants, namely the mean and the variance. That's it. That's what a Gaussian has. And otherwise, it has infinitely many non-zero cumulants. In particular, there is no distribution which has exactly 5 non-zero cumulants, or 7 non-zero cumulants, or 9. Either it has 2, mean and the variance, that's a Gaussian, or it has infinite non-zero cumulants. And anything which is different from a Gaussian must have an infinite number of non-zero cumulants. This is a theorem from probability. This is a theorem about probability, but the only proof I know of uses complex analysis. I don't think there's an elementary proof of this theorem without using complex analysis. And so what we did is like, basically at a very high level, what we did is that when D0 is not a Gaussian, you are guaranteed that while you do not have this equation as before summation Wi to the j, while you do not have this equation for every j or every even j, you at least have infinitely many of these equations. And once you have infinitely many of these equations, you can work with that to figure out what the vector, whether W is k-sparse or not. Okay, you do not have it for every j, but you have it for sufficiently many j's. You have it for infinitely many j's. So that, and so really like, the non-constructivity in the bound comes from the fact that Marcinkiewicz theorem just guarantees that there are infinitely many of these non-zero cumulants. It actually does not tell you where these non-zero cumulants are located. Even for explicit distributions, it doesn't tell you anything. So actually,
but then do you guys improve on the Marcinkiewicz theorem? That would be my question, but you already answered half of it. So how do you prove that you can even find one of these that is non-zero?
Well, I mean, I did not say we can find one of these. I said there's an infinite sample. I just said there's a finite sample complexity, which means there must be infinite non-zero cumulants. So roughly speaking, the sample complexity for general distributions will just say the number of samples will depend on where is the first non-zero cumulant and where is the second one located, wherever is the third one located. I know this is there is a well-defined answer as to where the third cumulant is located.
Mm-hmm.
Okay, so we do not give explicit answers in that sense. We just say it depends on what D naught is, so where the location of its non-zero cumulants are. If D naught is compactly supported, if D naught is a distribution which is not support, has a compact support, then we can explicitly get a version of Marcinkiewicz theorem. It's not great, but it's something. So we get some explicit bounds provided D naught is, and that's the tower of exponentials we get if D naught is compactly supported. Otherwise, our bound is just defined like how much. What's the sample complexity? Well, it depends on where the first non-zero cumulant is located, and then if you go after the first location, if you add 100 more, where is the next one located? After that, where do you find the 11th one and then the 97th one and so on? You know there's always an answer because there are infinitely many non-zero cumulants. So you know you can always go sufficiently high and find another one. I don't know if I answered your question really. But most of the proofs are, for general D naught, the proof is entirely non-constructive. We do not give a bound. We just say something dependent on D naught.
I see, thank you.
I think I'm out of time, so let me stop here. But if there are any questions, I basically did not say anything about the second part.
Okay, yeah. So let me. Okay, so I'll thank Anindya for giving this really great talk. So I'll clap for everyone.
Thank you.
I guess, yeah, and yeah, we can open for questions now. If you guys have questions, please.
Yeah, I don't know. This is super cool. Thanks for presenting this Anindya.
Thanks. Yes, it's like the bounds are. I think there's a lot of room to improve on the bounds.
Sure, yeah, but I mean, like, okay, I have in that regard. I mean, as an algorithm, like from the theory point of view, like, okay, you can improve the bound, but like the question is, will people care about tighter and tighter bounds? But like in terms of practice and practical algorithms, if that's what you care about, it sounds like pretty reason. Like, I don't know, it sounds believable that this could be something reasonable. Like, you know, you have some heuristic, like check some cumulants and see if they're what you expect or not.
Yeah, I mean, typically, like, typically what would happen is if we were not even dealing with the uniform distribution, if you were dealing, let's say, like, with some that, I mean, the fact that the cumulants, like, the reason why this algorithm has pathetic upper bounds is because you can have long deserts of zero cumulants. That's not typically going to happen. If you like, let me just say, like, if you generated a random distribution somehow on the real line, actually its first cumulant, its mean might be 0 or something. The variance is not going to be 0. The fourth cumulant is not going to be 0. The sixth cumulant is not going to be 0. So actually you will get pretty good bounds. It's actually only the case that the cumulants keep coming 0, which is like something that can happen, but you don't expect it to happen.
Yeah, that's really ridiculous. Okay.
And in
right.
some,
so for all practical purposes, your constant depending on d0 is k, essentially.
Yeah,
right?
yeah.
Like,
And I think for all
k.
of them, like, we basically should get like exponential in k sample complexity. And if you can improve that, like, for the I would start with the hypercube case where it's really nice. And then, like, potentially from that, you can show that essentially, like, if you can improve on that, potentially one can show that, like, some sort of smoother analysis that if the background distribution was not like, arbitrary, but like, some like smoothing was done, then the background distribution, then all the first 2k or 2k cumulants are all non-zero. So you should be able to get the same bound that you get for the hypercube.
Okay.
I wonder how limiting, like, okay, like maybe this is too practical for an ANC seminar, but like, I'm wondering how much of a drawback it is that it can't work under like Gaussian distributions, like, by some sort of central limit theorem, maybe like people would assume that their data distribution is Gaussian. And I'm wondering if like that would really arise, but this is...
I mean, I don't know. I mean, as such, like, it's not, we just showed that there's a log and lower bound for Gaussian. It might be true that even for Gaussians, you can improve on the learning bound. I'm not answering the question you asked me. I'm just saying k log n is tight for recovery.
Right, yeah.
That's just true. We haven't shown that, k log n is tight for the testing question for Gaussian. We just said for k equals 1, it must be log n. it might be the case that, it grows as square root k log n or something. That should be interesting. I think that would be interesting. Like if one can show that, in some sense, you can improve on the learning complexity in every setting.
I see.
Okay, so let me just thank Anindya again.
Thank you.
For everyone, so thank you very much. I'm just gonna stop the recording now, and I guess we can chat here for a bit more.